nomenclature variations as well. It's possible to have two alcohol groups present in a chain, and those substances are called diols. When we have that, they both alcohol groups need to be given a number. In this case, this is hexane 1,6-diol. So instead of a hexanol, it's hexane 1,6, indicating what again? Yeah, that the alcohols are on carbons 1 and 6. Okay. If the alcohols are side by side, and we should have seen this somewhere along the line, what do we call them?
This is.
They are diols, but they're called glycols. Okay, 1,2-diols are called glycols. Okay, as well. This one is not a diol. This thing, by the way, is used in the production of synthetic polymers. This 1,6-hexane diol.
You said 1, 2, but it can be
Yeah, they can. I could have a 1,4 or a 2,5, 1,6 in this particular case. But if they're side by side, it's called a glycol. Yeah, by 1, 2, I mean they can be anywhere in the chain, but they're next to one another. This one, as I recall, is used in a version of polyester. Glycols, as we just indicated, are where the alcohol groups are attached on adjacent carbons. This is ethylene glycol here, or ethane 1,2-diol. When we use the glycol name, we use the alkene from which the glycol would be derived. And in chapter 8 somewhere, you should have seen reactions where alkenes can be reacted with various reagents to form glycols. For example, osmium tetroxide, potassium permanganate, or a peroxy acid to make an epoxide followed by acid hydrolysis. All of those reactions produce side-by-side alcohol groups. And they start with an alkene. So the alkene that would have been the parent of this glycol would have been ethene or ethylene. So this is old style nomenclature, but it's very commonly used. So propylene glycol would be what? Glycol produced by using propene as the starting material. And I could react it with, say, osmium tetroxide followed by hydrolysis, and I would have two alcohol groups where the double bond once was. And that would be called propylene glycol. It could be a butylene glycol. Does that make sense? That's the pattern. This is propylene glycol here, we were just talking about. The IUPAC name for this would be ethane diol, you can see here, and propane 1,2-diol. Why the numbers on the propane diol? Because there is a possibility it could be 1,3 instead of 1,2. And we probably really don't need the 1,2 on the ethane diol, because there's really only two places for it to be, but it's commonly shown anyway. Okay. Phenol nomenclature. If we take away the chlorine here, this is phenol. And phenol nomenclature is based on using phenol as the base name. In this particular case, the alcohol group, because it's the top priority group attached to the benzene ring, is considered to be attached to carbon number 1. Then I number away from it, whichever direction is going to give me the lowest combination of numbers for other groups. So this is understood to be carbon number 1, and I can identify where the chlorine is by numbering that way or that way. And I'm going to get a lower number if I number clockwise. So this is going to be 3-chlorophenol. Unfortunately, the aromatic chemists are agreed upon. They have their own nomenclature systems as well. If I have two things side by side on the ring, that's called ortho. If there's one carbon separating them, it's called meta. And if they're across the ring from one another, it's called para. So there's ortho, meta, and para, and that's what that's showing. It's an alternative that's commonly used in organic chemistry. Only works for doubly substituted. If there's three things there, we don't use that. for rings that have two things on them, we use ortho, meta, and para. You understand that? Okay. And we'll see that later on when we get into the aromatic compounds. Now, here's phenol, and there's a methyl group out here. That's 4-methylphenol, or para. I wish I wouldn't get into this. But a methyl group and an alcohol group on a benzene ring has a common name called cresol. So that's para-cresol. What would meta-cresol be? Yeah, carbon would be carbon number 3, and orthocresol, right next door to one another. And so what you're getting here is a little bit of a preview to aromatic nomenclature. All right? Here's a problem, and it's pretty easy to see the answer here. It's right up there on the slide. We're asked to figure out an appropriate name for this alcohol. And one of the rules for naming this compound will be invoked here. One of the rules is we find the longest continuous chain that contains the alcohol. Notice that if I go along here, I've got a longer chain, but that chain does not contain the alcohol. Or if I go along here and down here, that's longer also. The longest chain that contains the alcohol is that one. You see what I'm talking about? And so that will serve as the base name. So we got 5 carbons, a 5-carbon group or 5-carbon parent chain with the alcohol group on carbon number 1. Can you see that? So it's going to be a pentanol, or a 1-pentanol. Now, attached to this chain, if this is carbon number 1, on carbon number 2 I've got an isopropyl group, and on carbon number 3 I've got an iodomethyl. Can you see that? So this will be 3. If a substituent like this is complex, we enclose it in parentheses and call it an iodomethyl. If it were just methyl, we wouldn't need the parentheses. You see what I'm talking about? And so this will be 3 iodomethyl, 2 isopropyl pentane, 1 ol. And there we're using the new nomenclature system.
And then if that second on carbon 2 that has the isopropyl, if it wasn't an isopropyl, if it was just a propyl?
Then it would be called N-propyl.
And O.
And some chemists would just put propyl. Propyl is understood to be N-propyl, attached on the end unless there's a designation.
And then that iodomethyl group, if they were both of the chains were the same, because you'll have 2 propyl groups. Yeah, it'll make, so that could either be 5 or this way 5, but this will have the iodomethyl. Which group?
Well, it's 5 only because of the alcohol.
1, 2, 3, 4, 5.
Yeah.
Right, but if it was like an N-propyl, it would actually be 1, 2, 3, 4, 5. It would be the same length as the other chain, right?
Yeah, it would.
And then what would determine?
Then what you would have here, this would still be your parent chain.
Because
But instead of a isopropyl group attached, it would be N.
why would that parent chain still be that one though?
Well, the parent chain has to contain the alcohol group.
Right, which it would.
He's asking why wouldn't it go,
I'm wondering, does the
why would
iodomethyl?
it just go straight down?
Yeah, because it'd be both 5 chain.
It's not a chain though.
If you move,
Well, I understand what you're saying.
Okay, sorry. I didn't
What you do here is if the chain can go 2 directions and it's the same length, then you find which has the greatest number of substituents
agree.
and go that way. Okay, and so if we're getting,
Yeah.
let's try it out.
Well, what kind is that? Here? So I got something. I forgot it.
CH236.
I was thinking the iodomethyl would make it.
OH, and then CH2, CH2, CH3.
Yeah.
Okay. Now, normally, and actually there probably wouldn't be a big fuss if we did it either way, but we could do it this way as the parent chain. or the way it's done here, which is this way. True? And they would be the same. So, if we did it this way here, notice we've got a really complicated substituent here. Can you see what I'm talking about? This guy right here would be a substituent to this chain. And it's still 5 carbons, but it's a single substituent. True? If I do it this way, then I've got that substituent and that substituent. And that would be what we would do.
Okay.
Does that make sense? This thing would be tough to name. That would be a,
Two small substituents rather than.
yeah, 2 small substituents is better than 1 big one.
Okay.
And this substituent, is everybody following this? This substituent right here, would be a 2, and then in brackets, we'd have to actually have a carbon number 2. It would be 2, and then in parentheses, and then in brackets, iodomethyl propyl. And I mean, we're getting really deep into the rules here.
So we'll naturally do it the easier way, which is the way that Teddy Packer did it.
Well, and in fact, by following the pathway that has the most groups, usually simplifies things considerably. Because easier to work with
Move on to what John
more
Francis
smaller groups than one big complicated.
I'll-
Are you okay
I'll
with
append
this?
those sections.
All right, and this kind of plays back into what we were talking about earlier. Physical properties of alcohols, because of the OH group, like we have with water, follow the pattern that water sets. They're going to have higher boiling points, higher melting points because of the hydrogen bonding that takes place, just as it is with water. In general, that effect diminishes as the hydrocarbon component increases in size. There comes a point about 5 or 6 carbons where the hydrocarbon component becomes the dominant feature, and the alcohol group's effects are lost. Okay, but for the small alcohols, they're water soluble, they have high boiling points, high melting points, they have high surface tensions. All of the properties that we see that water has will be shared by the smaller alcohols. And they'll be water miscible as well. Some boiling points here. Ethanol, a compound that has 2 carbons, is C2H6O, has a boiling point of 78. This is dimethyl ether, it's called. Notice that the oxygen here does not have a hydrogen that can participate in hydrogen bonding with other ether molecules. Look at the boiling point, 100 degrees lower. And yet, the formula is still the same. That's an indication of the powerful influence of the hydrogen bonding of the alcohol. And here's propane, which is not all that much different, but I've got carbon with 2 hydrogens instead of the oxygen there. And propane has a boiling point of minus 42. So the alcohol manifests its effects very dramatically, particularly in these smaller alcohols. Does it make sense?